All right, we're going to be talking about tries. Uh, let's talk about tries. What is a trie? A trie is a tree data structure that is used to store letter characters in each node that forms a string. Each node has up to 26 children, and 26 is not a coincidence with the alphabet, because each of those children correspond to a letter in the alphabet and their position in the alphabet. So A would equal 0, B would equal 1, Z equals 25, And at the end of a valid word, you'll usually see a marker to state that the word is ending. So in the word cat, T would be marked as end of word. And that's, yeah. It's a ON time complexity and O1 for space. Insertion is done in a little bit of a funky way. To find if a new child node is needed, take the character you're inserting and subtract it from A, which is 0. So if the number isn't present, i.e. you get null pointer, then you need a new child node. And if it is present, your string will follow the already existing path. So the insertion logic is your character minus A, which is 0. This is done because when you subtract your character from A, you're checking to see if that character is already present. Nodes cannot have duplicate children, meaning you can't have two X's or two B's as a child for a singular node. Yeah. We have an example. So you start with the root up here, and since the tree is empty, the trie is empty, B will be inserted as a child of the root, B, and it can be represented as child 1 because B would be corresponding to 1. Like I said earlier, A equals 0, B equals 1, C equals 2, and it keeps going. So child 1 would be B. Oops. And now we're going to insert O. B has no children, so new child node is needed for O. And it can be child 14 of B because O corresponds to 14. And when you insert N, it's the same thing. N would be child 13 of O. And then D would be child 3 of N. And for D, it would be marked as end of word for bond. So we have the full word. And you're reading top to bottom, B-O-N-D, you have that full word, bond. And since it's marked as end of word, it knows to stop there. So we're inserting born now, B-O-R-N. Since we already have a B of 1, B, which is 1, minus A, which is 0, equals 1. We already have a child 1, so we don't need a new child. And it will just go through the same path here. O is 14. We already have 14 for a child of B. So again, no new child is necessary. It'll run through here again. R, which is 17, the index 17, we don't have that. 17 minus 0 is 17. And we only have N, which is 13. So we'll need a new child for this. And then N, R has no child or children, so N would be put under R. This is marked as the end of word. So we have two different words, and you'll see, reading from top to bottom, for each of these words, they form a complete word. So if we wanted to insert bonds, it would be simple. See, we have B, which is already used, O, which is already taken, N, which is already taken, D, which is already taken. And then we would put S as a child of D because there's no children for D. And S would be child 18 of D. So if we inserted egg, what would that look like? Well, since there's only one child in the root, which is child 1, there's room for E, which would be child 4 of the root. And it would just be off on its own side. What are some practical applications for trees? Well, I thought the best application for a trie, I keep saying tree, I don't know why, but it's trie, The best application for a trie would be a search engine because, let's say you type in BA, right? You're going to get a bunch of different things that pop up that all start with BA. You're going to get bachelor, band, bark, etc. And with a trie, it's a lot more efficient because you don't have to scan like an entire dictionary for words. You just need to scan the specific parts of the dictionary that start with BA. So there's a lot less stuff you need to iterate through. And we'll check out some code that I wrote before. All right. So we have our code here. And I'll just show you how it works a little bit. So we have 5 words here: bat, bachelor, band, bark, eggs. And let's say we want to find every word in here that starts with BAN, right? So, oh, whoops. So let's fix that. So ban, it's going to pop up, and we only have band here that starts with BAN. Let's say I want to find every word that starts with E. We should just get eggs, right? And let's say we want to find every word that starts with D. We shouldn't be able to find anything here. There's nothing here for that to find, right? And there's no words. So how this works, we have the trie node, and then we have the trie class. So the trie node is pretty simple. It's just going to be a node. It has 26 children, right? And that's going to be an array of trie nodes, right? And we're going to have an isEnd marker. It's just a Boolean. This is going to be set to false by default because not every node is going to be the end, right? So if it is the end, we'll change it to true like we do down here. So we get down to the class. We have trie node root. This is just the root. It's just a trie node. We have insert. This is, like we said before, it's going to check to see if that node has any children that start with the letter that you're trying to insert. And if it doesn't have that letter, it's going to add a new child to be placed under that letter in that node. So we have, for character C, which is like just the characters, and then word, which is the string that we're trying to insert. All right, character is just a character from word, right? And it's just going to iterate through that. So C minus A, right? We have that. So it's just going to be this minus this, which is 0. So you're just going to check to see if the character's present. So if it's not present, it's going to add a new node. And if it is present, then it's just going to keep going until you reach the end of this. And then once you reach the end, this is obviously going to close. And the end, the last letter you inserted, is going to be marked as isEnd. And that's just to mark that the word ends there. Now for search, it uses find, which is down here. We talk about that. But it's just searching through the table for the node that or like the word that you're looking for. Starts with, it's just going to check. It's going to have this prefix here. And again, it's just going to check to see, which ones start with that character. And we'll get back to that and up there. So find, it's going to take this string and is going to iterate through this string, character C, and it's going to iterate from the top. So you're going to have same thing that you're doing up here, C minus A. If it doesn't exist, right, if you can't find C, right? If that doesn't exist, it's going to return nothing. It's going to return null pointer because you didn't find anything, so there's no point in returning anything. And if you do find something, it's just going to return node, right? That's what you want. You want to return the node, and then you're going to put that with the rest of the ones you find, and that's going to be in here. So collect words, it's just going to, if you get the node, and if it is the end, right, if it is the complete word, then you're going to want to put that with this vector of words to be returned, right, or to be displayed in this case, because we're not returning anything with this. Okay, so what this is going to do is going to iterate through the entire word, right, when it's called, and it's going to go through this node, and if it makes it through the entire thing and it says is end, you're going to push it back and you're going to store it in words. So you have like the words that start with the prefix, right? So when you call it from up here, starts with, you're going to have find prefix, right? You're going to call here. You're going to look for words that start with the prefix. And if you don't get anything back, then you're going to return nothing because you didn't get any, or well, you're not going to return anything anywhere, but you're not gonna have any words to display, right? And then you're going to go through all of the words you collected that would be a possible match, and if they work, then you're gonna have them stored in results, and then you're just gonna output all of them. So words that start with E should just get eggs, right? And this is just, it just shows, takes less time than a normal array, because you're just going through the words that have start with that. You're not going to have to iterate through the whole thing. It just sees, where is it? Sees, you look at the root, it's going to look for stuff that starts with E. And so it's going to see that this starts with E, so it's just going to go down here, as opposed to, it's going to see right here that you have a B, so it's not even going to bother going through these 3 words here. So it saves time, you don't have to go through here, you just have to go through here. And it kind of works like a BST in that way, right? Yeah, I think that's right. Yeah. All right, so those are tries. They're pretty cool. I like to think of them kind of as like the BST for strings. I mean, it's definitely not 1-to-1, but that's the best way I can think of it. So yeah, thank you. Have a good one.